What if the secret to unlocking quantum computing's game-changing power isn't building better quantum machines, but instead teaching them to work alongside the supercomputers we already have? Researchers at Oak Ridge National Laboratory have just dropped a bombshell that could reshape the entire future of computational science. Their latest breakthrough isn't a new quantum processor or a faster supercomputer. It's something far more intriguing, a comprehensive software blueprint that promises to merge quantum computing with high-performance computing systems in ways we've never seen before. But here's where it gets controversial. Some experts argue that this hybrid approach might actually be holding back pure quantum development. Are we settling for a compromise when we should be pushing quantum technology to stand on its own? The revolutionary partnership nobody saw coming. The scientists at ORNL have developed what they're calling a flexible software framework that acts as a universal translator between quantum processors and traditional supercomputing powerhouses. Think of it as creating a common language that allows two completely different types of computational brains to collaborate seamlessly. This isn't just theoretical wishful thinking. The research team has laid out detailed plans for connecting these technologies in ways that could potentially unlock scientific breakthroughs we can barely imagine today. We're talking about revolutionary advances in everything from understanding molecular behavior at the atomic level to creating accurate models of our planet's climate systems. Quantum computing, despite all the hype, remains frustratingly limited in its current form. These machines operate on principles that seem almost magical, using quantum bits or qubits that can simultaneously exist in multiple states, a phenomenon scientists call superposition. This unique ability theoretically gives quantum computers access to computational possibilities that dwarf anything traditional computers can achieve. However, and this is the part most people miss, quantum hardware by itself simply isn't robust enough yet to tackle the massive, real-world problems that scientists desperately want to solve. That's where the marriage with high-performance computing becomes not just useful, but absolutely essential. Learning from past computational breakthroughs, the ORNL team draws inspiration from a computational revolution that many people take for granted today: the pairing of central processing units with graphics processing units. This CPU-GPU combination transformed computing capabilities and directly enabled ORNL's Frontier supercomputer to smash through the exascale barrier back in 2022, achieving mind-bending speeds of over 1 quintillion calculations every single second. But here's the intriguing parallel. Just as GPUs weren't originally designed for scientific computing, but became indispensable accelerators, quantum processors might serve a similar role as specialized accelerators within hybrid computing environments. The 4 pillars of the hybrid computing revolution. The ORNL blueprint centers around 4 groundbreaking software innovations that work together like pieces of a sophisticated puzzle. First, they've designed a unified resource management system that can intelligently coordinate both classical and quantum computational tasks. Imagine having a super smart traffic controller that knows exactly when to route calculations to quantum processors versus traditional systems, optimizing performance across the entire hybrid setup. Second, their flexible quantum programming interface acts like a universal remote control, hiding all the messy technical complexity that usually makes quantum programming a nightmare for developers. This means programmers can focus on solving problems rather than wrestling with hardware-specific quirks. Third, the Quantum Platform Management Interface provides seamless integration capabilities for diverse quantum hardware types. As new quantum technologies emerge, and they're emerging rapidly, this interface ensures they can be plugged into the existing framework without requiring a complete system overhaul. Finally, their comprehensive toolchain optimizes and executes quantum circuits with maximum efficiency, squeezing every bit of performance from these delicate quantum systems. This modular, layered approach means that as quantum technology evolves, and it's evolving at breakneck speed, the entire system can adapt and grow without becoming obsolete. The quantum Achilles heel. Here's the brutal truth about quantum computing that the tech world often glosses over. Qubits are incredibly fragile and temperamental. These quantum bits lose their special properties almost instantly when disturbed, leading to error rates that would make traditional computer engineers weep. Currently, quantum systems are limited to solving relatively small-scale problems because of this fundamental instability. Different research teams worldwide are pursuing wildly different approaches, some betting on neutral atoms, others on superconducting circuits, trapped ions, or exotic materials. Yet no clear winner has emerged from this technological horse race. And this is the part most people miss. ORNL's software architecture is specifically designed to thrive in this uncertain landscape. Rather than betting everything on one quantum technology, their framework remains agnostic, ready to embrace whatever quantum breakthrough emerges victorious. Building on solid foundations, this latest research represents the evolution of ORNL's earlier theoretical work, exploring Quantum-HPC integration strategies. While their previous studies focused on conceptual possibilities, this new blueprint provides concrete, actionable guidelines that engineers can actually implement. The heart of their approach revolves around something called a quantum controller, essentially a sophisticated interpreter that facilitates communication between quantum processors and supercomputers. This controller handles the intricate dance of scheduling tasks, managing data flow, and ensuring optimal performance across both computational realms. The Unified Resource Management System takes this coordination to the next level, preventing performance bottlenecks that could derail the entire hybrid operation. It's like having an incredibly sophisticated conductor orchestrating a complex symphony between two very different types of instruments. Unlocking scientific possibilities beyond our current imagination, the potential rewards for successfully merging quantum and HPC systems are staggering. The ORNL team believes this combination could trigger a computational revolution similar to the CPU-GPU transition, but potentially even more transformative. Consider this mind-bending limitation. ORNL's Frontier supercomputer, despite being one of the most powerful machines ever built, can theoretically simulate only around 50 to 60 qubits due to the exponential complexity of quantum calculations. Meanwhile, actual quantum processors are already handling hundreds of qubits with increasing sophistication. This hybrid approach could demolish current computational barriers, making previously impossible problems suddenly solvable. High-resolution molecular simulations, complex optimization challenges, and advanced machine learning applications could all experience exponential performance gains. But here's where opinions diverge sharply. Critics argue that this hybrid approach might actually slow down pure quantum development by creating dependency on classical systems. Are we building a bridge to the quantum future, or are we creating a crutch that prevents quantum computing from reaching its true potential? Navigating an unpredictable technological landscape, quantum computing's ultimate configuration remains shrouded in uncertainty, with current prototypes potentially bearing little resemblance to the dominant technologies of tomorrow. This unpredictability makes ORNL's emphasis on flexibility not just smart, but absolutely crucial. Their proposed framework prioritizes modularity above all else, ensuring that revolutionary breakthroughs in either hardware or algorithms can be incorporated seamlessly. The team envisions a dynamic software ecosystem that grows and adapts alongside both quantum and classical computing advances. By focusing on what they call performance portability, the framework empowers programmers to develop hybrid applications that will remain functional and effective even as underlying hardware technologies undergo dramatic transformations. The global race heats up. As international competition intensifies, similar hybrid computing initiatives are gaining momentum across Europe and Japan. ORNL's blueprint doesn't aim to monopolize this technological frontier, but rather to catalyze collaborative innovation throughout the global research community. Their ultimate objective is establishing a robust foundation that accelerates breakthrough discoveries and ensures that quantum-HPC convergence delivers maximum societal impact. If this ambitious vision succeeds, the fusion of quantum and classical computing could represent humanity's next exponential leap in problem-solving capability. We might soon witness computational advances that enable precise atomic-level molecular interaction simulations and comprehensive modeling of entire planetary systems. But here's the million-dollar question that nobody wants to address directly. What happens if this hybrid approach becomes so successful that it actually discourages investment in standalone quantum computing research? Are we potentially creating a technological dead end disguised as innovation? What do you think? Is ORNL's hybrid strategy the brilliant bridge we need to reach quantum computing's full potential? Or could it become a comfortable compromise that prevents us from achieving true quantum supremacy? The future of computational science might depend on how we answer this question, and frankly, the experts themselves are still divided.